Hello everyone, I hope you guys are doing well. Now we are in continuation of the previous lecture for the exact differential equation. So before going to study further, I request each and everyone subscribe, like and share the video, okay, and press the bell icon for the further notification, okay. So now I'm going to the further study about the exact differential equations. So now we talk about the integrating factor. What about the integrating factor? So I'm writing here the definition of the integrating factor. An equation of the form mdx plus ndy need not be an exact an exact differential equation. An exact differential equation. Now to make it exact, we need to multiply a factor of x and y so that the given differential equation reduce into the exact differential equation. This multiplier is called the integrating factor, right? Integrating factor. Okay, this multiplier is called the integrating factor. One more remark I would love to introduce here. Remark. Although an equation of the form mdx plus ndy equals to 0 has always an integrating factor. So there are several rules to find them. There are several rules to find them, okay. What about the rule number 1? So rule number 1 I would love to explain here. If the given differential equation is homogeneous, right? If the given differential equation mdx plus ndy is equals to 0 is homogeneous, then integrating factor will be decided as 1 upon mx plus ny, right? And this should be non-zero. Mx plus ny should be non-zero. Then your integrating factor will be decided. After finding this integrating factor, just multiply this in the given differential equation mdx plus ndy, and then it is first class exact. And after converting it into the exact differential equation, you can find simple solution with the formula of the exact differential equation. So I'm going to here we have given a differential equation. Okay, we need to check it out about the exact, is it the exact differential equation or not. Okay, so now comparing the given differential equation with the general format mdx plus ndy. Okay, so on comparing with the general format, we write here the value of m. What about the value of m? Value of m is x square y minus 2x y square, and partial differentiated with respect to y, so it is del m over del y, and which can be written as x square and minus 4xy, right? And now we write capital N, so capital N will be written as minus x to the power 3, right? And minus 3x square y. So your partial derivative with respect to x will be dealt as del n over del x, so it is minus 3x square and minus 6xy. Okay, minus 6xy. So what about the relation? Obviously del m over del y is not equals to del n over del x. Okay, del n over del x. So this implies that the given differential equation is not exact. This implies that the given differential equation is not exact. Is not exact. If it is not exact, then what about the integrating factor? Because every differential equation of this format has an integrating factor, then we need to find the integrating factor. So first of all, see the given differential equation. Obviously the degree of this term is 3, and degree of this term is also 3, and degree of this term is also 3, and degree of this term is also 3. So this implies that the given differential equation is homogeneous, right? The given differential equation is homogeneous. Now if it is homogeneous, then what about the integrating factor? Then the integrating factor will be decided by 1 upon mx plus ny, right? What about the mx plus ny? So 1 upon, what about the m? M is, x square y, so multiply by mx, so it will be x to the power 3y, right? And minus 2x square y square and plus ny. What about the n? So n is this, so x to the power 3y, right? And it is minus with minus sign, and then plus 3x square y square, right? So what about the resultant? It is cancelled out. What about the final? So we need to write here, I think it should, therefore the resultant is first class, it is 1 upon x square plus y square. Okay, so it is the integrating factor. Now we multiply this integrating factor in the given differential equation. So come on, what about the resultant? And we have the given differential equation as x square y minus 2xy square. So x square y minus 2xy square, and multiply by this factor 1 upon x square and y square dx, right? And then what about the next? Next is x to the power 3, 3x square y. x to the power 3 and minus 3x square y. So it is also multiplied by 1 upon x square and y square is equals to what? It is equals to 0, right? So dy is equals to 0. So what about the resultant? So resultant is, multiply x square y by square inside. So we write here 1 upon y because it is cancelled out, right? And similarly in this term minus, so 2 divided by x, 2 by x, okay, because y square is cancelled out, and x the power 1, okay, dx. And minus, what about this? So here we have x upon y square and then minus 3 upon y dy is equals to 0. So it is first class now exact. It is converted or reduces it into the exact differential equation. So what about the solution? Obviously it is your m and it is your n. So now come on, write here the value of m, 1 upon y minus 2 upon x dx, keeping y as a constant, keeping y as a constant. So we have the very simple methodology, right? And what about the n? Only those term of n which do not contain x. So we remove this term. So here we have minus plus 3 upon y dy is equals to 0. So what about the integration? This integration we have 1 upon y as a constant. So you can write x upon y. The integration of 1 upon y is x. The integration of this is, minus 2 log x, okay, and then plus, what about this, 3 log y. So we are having here number of terms in terms of the log, so you can treat your constant also as log c, okay, and you can write it as in the combined form x upon y, okay, x upon y minus or you can write it as plus log 1 upon x square and plus log y is equals to log c. And finally you can explain it as x upon y and then plus log y upon x square is equals to log c. So it is your final answer. You can stop here. Okay, so guys, we have the simple methodology and simple steps to solve a reducible exact differential equation into the exact differential equation. So it was about your rule number 1. If the given differential equation is homogeneous, then we will reduce it as follows. So I request each and everyone keep watching these videos, and I'm again requesting share, comments, like, and press the bell icon each and everyone, and subscribe the channel. So see you in the next video lecture. Thank you very much.